So the TAU performance system is a parallel profiling and tracing toolkit that supports or aims to support all the HPC platforms and different languages and compilers and runtimes. So we have automatic source instrumentation capabilities in TAU to target C, C++, Fortran, and Python, as John just mentioned. We can instrument at the level of different runtimes like MPI, OpenMP, Cocos, pthreads, and we have many ways to insert hooks into your program, and we'll see some of these examples. Once the instrumentation or hooks are inserted, you can generate performance data in the form of profiles, which are summary statistics, or event traces that show you the details of where every event takes place on every process. And then we have some analysis tools such as ParaProf, Perf Explorer, and we can also export data to other tools such as Vampire, the Vampire Trace Visualizer. We support many different languages, runtimes, and we have these analysis tools that you can use. We'll see that in the hands-on session as well. Well, you're probably wondering, what can TAU show you? It can show you where the time is spent in your different application code regions, such as routines, loops, right down to the statement level. You can also see what is happening inside system libraries and other libraries for which you may not typically have the source code. You can see the symbol information from there as well. Instead of time, you can also see other metrics, such as the number of floating point instructions, or data cache misses, or total cycles executed. You can, for example, measure what is the extent of vectorization of loops. You can measure the memory usage of your code. You're probably wondering, what is the total memory used in my application, which includes the stack, text, data, BSS, and heap. You can see that memory footprint. You can also see where memory is allocated, deallocated, if there were leaks, what is the high water mark for the memory usage, how much the energy is used in the application, the I/O characteristics of your code, such as the peak, read and write bandwidth. You can see the contribution of each phase of your application and also how it scales. So there are different phases of inserting hooks in your code. The first one, the instrumentation phase, allows you to add these hooks. You can add these hooks using a preprocessor in your code. And we use a toolkit called Program Database Toolkit to parse your source code and insert hooks in a copy of your source. We can also use compiler-based instrumentation to add hooks. Again, we use compiler scripts instead of the original compiler to add these hooks. We can also use runtime preloading, which allows you to transparently insert hooks into a dynamic executable. Now, this is an interesting option because you don't need to change anything in your code. You can just compile it. In the case of theta, you should compile it with -dynamic and just run it with a script called TAU exec. And it will generate the performance data for your application. It can generate profiles as well as traces. The key difference is profiles show you how much total time was spent in your application, while traces will show you when the events take place because it creates a time-stamped log of events. So if a function foo is called 100 times, in a profile you just see the total sum of the time spent in foo across all 100 invocations, whereas in traces, it will create a start and stop time for each of those 100 invocations. So the size of the trace can increase as you call the event frequently and as you increase the number of processors and the time for execution. Now, one thing which we'll see a lot in TAU is the exclusive time and the inclusive time. I would just like to take a minute to reiterate this. If there's a function called foo which takes say 100 seconds, and it calls another function, say bar, which takes 20 seconds, then the exclusive time spent in foo is 80. It's the total time less the contribution of any instrumented function. And instead of exclusive and inclusive time, you could say exclusive or inclusive data cache misses or cycles or any other metric. But that's an important thing. If you use timers that are inserted as hooks at the start and stop with direct instrumentation. This is the start and stop direct instrumentation using probes, where there's a call to a function where entry and exit is recorded in the source code. You can also use indirect measurement using sampling, where we collect a number of samples and estimate the total time spent in a function. As an example, suppose your application runs for, say, 100 seconds, and you take a sample every second and collect 100 samples. If there is a point in your code, in, say, a function called foo, where you collect 30 samples, then you could estimate and say that, well, 30 seconds were spent in that location. Okay? So that's the sampling approach, and this is the direct instrumentation approach. This is how it looks. You create an interrupt, and this periodic interrupt is generated by the system timer or the overflow of some hardware performance counter in the system. And you generate this interrupt periodically, you measure the number of times you receive the interrupt, and create an estimate. With instrumentation, you insert the code directly in a function. So you have a start and a stop call like that. And then, based on this, you must create a profile that shows the total exclusive and inclusive time for the measured elements. We have a tool called TAU exec that can preload a library and insert the hooks for instrumentation. Now, we can do this for a variety of different runtimes and make different measurements, such as we can tell you how much time was spent in MPI calls. We can show you the time spent in OpenMP calls, in POSIX.io. You can look at the memory allocation, deallocation. You can also wrap another library and insert the hooks in that. You can also enable other options in TAU, such as event-based sampling, generate OTF2 traces, you can generate communication matrix, and all the measurement options that TAU provides. But what is important to note here is you do not need to change your binary at all. And you probably have many codes that you have used over the last several days, which use a combination of MPI with OpenMP, and you're probably looking for a tool where you do not need to modify anything, and you can precisely tell how much time is spent in MPI, in OpenMP loops, go down to the exact loop, and also at the source statement level, where you can measure exactly how much time is spent in each statement. So this simple tool will be able to address those issues. Let me just say how this TAU exec works. So if you look at the top, if you're running your code like this, ap run -n64 a.out, you can just say TAU exec a.out, and it will show you the time spent in MPI. You can say -ebs or event-based sampling, and it will show you the time spent in individual statements in your code. If you want to change the period of sampling, you can specify that. You can also specify a different hardware performance counter instead of wall clock time to get the interrupts. For example, you could say PAPI L1 DCM to measure the PAPI level 1 data cache misses, and a period, an overflow count of, say, 1,071,000 or some prime number which is big. Here is an example of using TAU to track I/O with a configuration specified by tags such as MPI, PDT, PAPI, and you can measure the I/O contribution of your code like this. Now, John mentioned the excellent work they have done to get the instrumentation hooks in OpenMP runtime. That has always been very difficult. MPI has been easy for tools to handle. OpenMP instrumentation is really tough. And he mentioned that many compilers will be coming up with the support for OMPT in November this year. Well, we have a preview over here where you can substitute one library with another, a substitute an OpenMP runtime which already has hooks enabled. And using this approach, you can see the exact time spent in all the OpenMP functions with unmodified binaries. This is thanks to the recent work that has happened in the TR6, Technical Release 6 of OpenMP standard, which was just released last year in November 2017. And this is a preview release of that, which allows you to measure the time spent accurately on all the threads and specify exactly which for loop the time is attributed to. You can also change the support level. Instead of full, if you use the default, you will just get hooks on thread 0 instead of threads 1, 2, 3, and others. You can also specify how addresses are resolved at runtime or later on during the post-processing phase. There are memory operations that you can track. You can also load another library like this. The important thing to remember is that this approach substitutes one library for another. You need to compile your program with the -dynamic flag to create a dynamic executable, because you're injecting a shared library in the address space. And I have a simple example over here where I'll show you how we can look at the performance of an application. You can use qsub. I'm sure you're familiar with how to get an interactive node on Theta, and you must unload this darshan tool and then load the Intel module and load the TAU. I believe you all have the slides, right? So you can cut and paste some of these things over here and run the code. And let's try this in a real hands-on session. I'll just do a demo right now. You can follow along and just look at the code later on in the hands-on session. So here is make clean. So here I just compile the code, make-j. I'll get a binary, and I'll just run this the way I can go to config suite.s this and look at the bin directory. Make clean and say make suite -j. So I'll say make suite. This is the NAS parallel benchmark. You may have used this before. It's the BT benchmark. And let us just go and run this code. So you export the number of threads, and then you can say n16-d4-j4 and then bt mz. This is running the application without any instrumentation hooks in it on 16 cores. Okay, and you're using 16 cores, 16 MPI ranks, 4 threads, and you're just running this code, and you're probably wondering, I've got 64 threads of execution. Where is the application spending its time? How much time is being spent in MPI? How much time is being spent in OpenMP? What parts of the application are being exercised as it's running? What compiler options did I use? Well, I used the latest Intel compilers. I use the O3 compiler options. Is it running at full speed? What can I do to evaluate the performance of this code? Right? How can I use this tool? So it ran in how much time? About 54.86 seconds, about a minute. To use TAU, as I showed over here, you can use event-based sampling, you can use OpenMP instrumentation, you can use a combination of both. So I can just cut and paste over here, and I say export this, resolve this address like this, module load TAU. So I get which TAU exec in my path. It's coming from here. And then, instead of running it like this, I will just say TAU exec and some tags. And here I can say OMPT TR6 MPI -EBS -OMPT, and I run this. So now I'm saying I want to measure the time spent in MPI. I want to measure the time spent in the OpenMP regions using the OpenMP tools interface. And I want to measure at the statement level what happens in the code. I did not need to modify the binary in any way. And I can observe the events in MPI and OpenMP using TAU. There is a program called ParaProf that I'll use to launch the viewer, the graphical interface. And I can use this GUI either directly on the backend node, or I can just transfer the files over. And ParaProf has a command, and it is, you can say paraprof pack the files with a -- pack, and you can say npb bt 16.ppk, something like that. Okay? And you will see there are profile files created, one per thread. Now, instead of bringing all of those profile files to my laptop, I can possibly just put it in a ppk directory, create a file over here, a single file, and let me just bring this one file over to my laptop and say scp theta ppk npb bt 16.ppk. Okay? And here, now I can launch the paraprof viewer. This will tell me where the application spent its time. If I click on node 0, thread 0, it shows me that out of 1 minute, it spent 31 seconds in a function called schedule yield. 31 seconds. It spent 23 seconds in wait all. And this is like the NAS parallel benchmark optimized code. Okay? If I say, well, was this just on the same one single thread, or was it on all the threads? On some threads, it's even worse. Okay? It's 31 seconds. So clearly, I forgot something. Okay? I didn't launch this correctly. I didn't use CPU affinity, right? And if you, look at the web pages, tips for running programs, running jobs in XC40, job submission, right there, I look at these options. And it says the CC argument specifies CPU affinity. Okay? When using AP run, you should always use CC depth. CC depth. Okay, let's see if that makes a difference.
What does that do?
So it basically makes sure that the threads remain on the same CPU and they're not being scheduled out and about just like what was happening over here, right? The 50 seconds, the 30 seconds, we were just spending all that time in that 1 minute. So let me just remove these files and run the same code again. But this time, let me just add this one option, CC depth. Okay? Does that make a difference? You're probably wondering, I'm iterating with different options, compiler options, runtime options, options to the job launch script. What's the difference? Where is the application spending its time? And then we can look at the performance of the code and compare one with the other. Okay? It will again generate profile files. I'll get 64 profile files that I had deleted earlier. And I will now see how much time it spent. Oh, look at that. The time spent, it went down dramatically. Okay? If I look at the profile files, and if I say pack, ppk, bt, npb, bt16, depth, okay, .ppk. So let me just call it this. And then over here on my laptop, theta ppk here. And now let me just launch, here, let me get rid of this previous one, npb bt16 star.ppk. So I'm saying the old as well as the new, just load them both in paraprof. And paraprof will load up both of these application functions. This is the depth one, and this is the original one. If I click node 0 here, I see the 31 seconds over here. If I click this, I see work. Oh, great. Look, it's showing me exactly which why solve parallel region in this exact line of code. Ysolve.f at line number 52. Okay, here is solve.f bin cvrhs. It shows me the exact lines, and it's doing good work over here. Compute RHS, this is what I wanted to see. Instead, I was seeing this because I missed that option. And very often, we don't read the user's guide carefully. Right? We don't read the things that they specifically tell us to do on the web pages. But the performance tools can show you where your application is spending its time, and it can also go down to the system libraries. It can show you exactly what was happening at like this function. This is a call MPI ch3i progress, which comes from libmpitch.so from MPI Vedal. It has gone inside the MPI library whose source code I do not know. I do not have access to these things, but it shows you all the different schedule yields and Vedals and all that. And I can measure exactly what the application was doing. I can also see this in a 3D view. And I can see exactly what each rank, each function, and application routine was doing in a 3D view like that. Here is the function slider, and then we have the thread slider over here as well, like this. And we can zoom in and look at every function in the 3D view. So here, another interesting feature is if you want to compare the applications, you could say, let's take thread 0, right-click on it, and say, add this thread to a comparison window. Okay? This is the time spent in different events on threads, thread 0. If I want to compare it to, say, node 2, thread 3, I can just add it over there. And then I can see over here the implicit task, the work distribution and all this, the barrier release. You can see in detail. Now, if I just add this thread 0 from the other previous profile, you will see that, oh, look, here the time was all dominated by schedule yield. And now it has gone down from 31 seconds to 1.1 seconds. The wait all has gone down from 23 seconds to 2.1 seconds. Right there, you can see a big difference. And you can observe the time spent in every single for loop at the location and the actual samples, like this sample or the sample in the source code. Another interesting view is you can just right-click here and say, show thread statistics table. And here it opens up and it shows you all the routines. And you can see, you can click on the inclusive time like this and say, OK, it spent 25 seconds. And in the Y-solve, it spent 6.5, 6 seconds in X-solve, Z-solve spent roughly 5.9. You can open it up, and here you can look at what's happening inside the loops, okay, like here. And this is the bin v RHS. So out of the 6.57 seconds, 3 seconds were in this, 2.9 seconds were in this, 0.45 seconds were in mult substitute. You can open up this and see exact lines of code where the time was spent like this. It says that line number 449 in the solve subs.f, it spent 0.25 seconds, and all of these times accumulated to create a summary which is about 3 seconds. If I try to say, show me the source code, I'm on my laptop. What will happen when I do that? It should say that it's not there. The source code is not there. Do you want to add it? And if I say yes, and if I find the workshop tarball and just bring it over, I will be able to do that. Here is the workshop tarball, and here is the NAS parallel benchmark. I can just click on BT and click select, and then close. And then it shows me the exact loop where it spent that time. And you can see over here what it was doing at that point in time. And then this remains for the other functions as well. So I could go down to a loop, for example, here, open the zsolve here, and then say, show me the source code, and it will just jump to this line of code. And it says, this is the line of code which took 0.35 seconds, right here. Okay? So you can jump right into an OpenMP code. You can go right exactly into a particular line of source code. You can go to like this solve and say, where is this solve? Show source code, and it goes to this OpenMP do loop. It doesn't go to the OpenMP parallel. It goes to the loop, exact loop, and says, this loop cost you 6 seconds. Okay? Now you can see the exact time spent in MPI functions. You can see the exact time spent in OpenMP calls right down to the source code. And you can see the time spent in individual statements. And all you had to do was say ap run, correct arguments, tau exec, a.out. Okay? You have some MPI applications with OpenMP. If you just cut and paste those commands and say module load tau and say ap run, tau exec, a.out, you will be on your way to generating the profile files. You can just say paraprof if you're okay with the, the X windows over your network, or you can also install TAU on your laptop and do what I just did, where I SCP'd a packed profile over to my laptop, and then I just launched it over here. Your source code needs to also come if you want to go down to the source level, but if you don't want to see the source, you can just do the rest of the analysis. So this tells us how to do performance evaluation on OpenMP with MPI. There are some other aspects to TAU with use with other languages, such as Python. With Python, we have a tool called TAU_Python. So instead of saying Python a.py, you could just say TAU_Python with the same set of options like we did with TAU exec, and then a.py, and it will use that. It will be able to use it on say deep learning frameworks like TensorFlow and pthreads and other executions. So with this, let me just get back to this and continue with our. So all I did here is set the OpenMP number of threads. I removed Darshan. I said module load Intel TAU, and then support level is full. Resolve the addresses, say TAU exec, and I added the EBS flag over here, just like we were showing you over here with the TAU exec event-based sampling. This shows me the line numbers because it's using the sampling. Without the EBS, you'll just get the full profile with OpenMP information in it. And this is the NPB benchmark. You can read more about it later. The TAU exec tool with the different options and how you use it. And this is step-by-step figures of paraprof that will show you how I used it. I used TAU exec, EBS. Don't forget the CC depth over here, okay? And then try running the application. This is just showing you the different flavors of TAU. We have a limited profile on one hand where you can just say, I want to instrument a few functions. You have a flat profile, a loop profile, a call site, call path, and then a full trace. The difference is, in a flat profile, you do not see the parent and child information in functions. You just see all the functions in a given execution. With a call path profile, you can see the edges. There are two environment variables, TAU call path and TAU call path depth. You set this to 1, and then you can set the depth to, say, 100, and you'll get call paths that go all the way to the root node. Call site profile is different from call path profile. The key difference is, if I run an application, and similar to what I just saw earlier, if it says MPI barrier accounted for 80% of the total time in the application. Okay? Now you say that's terrible. Okay, which MPI barrier? Then you turn on TAU call path equals 1, and it will show you that MPI barrier called from, say, the solve routine took 80% of the total time. And then you do a grep in the solve routine, and you may have 5 instances of MPI barrier over there. Very bad, but still. If you have those 5 instances and you said the contribution of MPI barrier from solve is 80% of my total time, which one of these solve, which instance of this solve is responsible for the most time? Then you can turn on TAU call site equals 1. And if you run the program again, it could show you that 75% of the total time came from solve at line number 12, where it called MPI barrier. And 5% of the total MPI barrier time came from the other 4 locations. So then you could go to the line number 12 and just comment it out and try running the code and see how it does. Right? So that's one way to look at the call site profile. You're looking at the location, the precise location in the source code where your application calls a given function. The phase profiles are interesting that you can annotate the code with distinct phases, and then you can see the time spent in the application based on those phases. For example, if you have a code where you say, I don't want to measure the time spent in, say, MPI bcast during the initialization phase. I'm reading from a file, sending it to everyone. I understand that. Show me what happens in the solve phase. And if you look at the output of your code, you will see the distinct phases right there, and you will be able to instrument it accordingly. Here is an example of the paraprof profile browser. You can see this is a flat profile. This is how you use the thread statistics table. You can click on that. You can right-click, say, show source code. I just have views here that show you exactly what I did. Here's an event-based sample profile. You can enable that with TAU sampling or TAU exec-EBS. You can unwind the call stacks too. This is very expensive, but if you want to do that, where you get a sample, you can say unwind the call stack, and then you can go right down to the lower level cray function, which is getting called in this MPI receive, and see exactly what was the call stack at a point where a sample gets taken. This is a call site profile that says MPI receive took 14.6 seconds, but this call site in exchange 1 accounted for 12.6 out of those 14 seconds. You can also see other thread call path relations windows. Here are context events that can show you how much time was spent in I/O operations, as well as the volume of I/O along a given calling sequence. This is a Python application calling functions, and you are looking at the time spent, the exact I/O performed in the different application routines. The 3D viewer, you can see call sites. You can also do source instrumentation using TAU, where you insert instrumentation hooks. You need to just specify a TAU Makefile environment variable and set TAU options. And when you configure TAU and install it, you will see that it creates a TAU stub Makefile which has different options. These options correspond to what configuration of TAU is used, and you should match this with your application. So you could see that with the Intel compilers, you can have MPI or MPI with OpenMP or MPI with pthreads and so on. And you can see that these tags are pretty much the same as what we specified in the Makefile names. There are options that you can specify for compiling the code in TAU options. You also have source instrumentation, selective instrumentation files that you can create, so you can exclude instrumentation in certain functions. And you can automatically do this by creating selective instrumentation files based on throttling of lightweight routines that are called frequently. TAU disables the instrumentation in these lightweight routines. You can just create a selective instrumentation file and re-instrument the code. We have other advanced TAU MPI interaction that you can capture through the MVAPICH MPI tools interface. And there's some very interesting work where you can change the knobs within the MPI runtime automatically and select the right options. MPI has many configuration options, but you can set this at runtime through a TAU plugin interface. You can read more about it in Srinivasan Ramesh's paper, and he's here at AppSec if you would like to talk to him. And create this TAU plugin and change the MPI execution by accessing the performance variables and control variables within MPI. And you can see the difference in performance when that happens. Here are some execution scenarios. I will not go into this in detail, but just I want to say that using this, we could reduce the time spent in MPI significantly. This is before, this is after. This is being shown in the Vampire tool, which comes from TU Dresden. And TAU can generate OTF2 traces with and target the Vampire tool directly. So there's less overlap here, there's more overlap over there. We also have a tool called TAU Commander. I will not go into this details right now, but we have simplified the workflow of TAU. So all you need is a single command called TAU. And you can just put TAU in front of everything and see what happens. Okay? You'll be very surprised. There's a very good TAU dashboard which can show you all the options of TAU. So you don't need to remember all the options I specified. There's a context-sensitive help, and you can see the different runtime variables that are available in TAU. You can download TAU from this web page. There's also an ECP PMR SDK container that you can download, which has TAU built in it with many other tools like Cocos and MPI. You can download TAU from this URL. We are located here at the University of Oregon in Eugene. We have a very good visitor program. Please come and visit us for a few days if you would like to work on TAU and talk to me about it. I would like to thank our sponsors, Argonne, Department of Energy, Department of Defense, the National Labs, National Science Foundation, NASA, CEA, and our partners at Ohio State University, the folks who make MVAPICH2, ParaTools, University of Tennessee, Knoxville for PAPI, TU Dresden, Germany for Vampire, and Euless Supercomputing Center for Scorpy, Opari, and many other interesting tools. Thank the Exascale Computing Program. Any questions, real quick? Or we can take them in the break.
The MPI tools interface that you talked about,
yes,
that is part of the specification, right? So,
yes.
So ideally, we can use any MPI implementation.
Any MPI implementation, yes.
Not only MVAP.
Not just MVAPICH, but the question is, MPI tools interface is a bridge that allows the runtime to communicate with the tools. But the runtime may choose to provide 0 performance variables and still be compliant with the MPI standard.
Oh, okay.
Okay. If you look at Intel MPI, they may not provide the performance variables. MVAPICH2 may open up the internal variables. So for example, if you wanted to find out, not just at the MPI level, but what is the level of congestion at a network interface? How many packets are queued up? Is it 10 or is it 10,000? The performance variables in MPI tools interface will show you that, only if they choose to export that. Okay? Yes?
So I saw there's support for GPU profiling and Cocos profiling. Is there support for Cocos using GPUs?
You know, I have used Cocos with OpenMP, and we have support for the OpenMP tools interface, the Cocos profiling interface. And it's just a question of trying it with a GPU. I do not believe there would be problems, but if you face any problems, please talk to us with Cocos. You should be able to just say tau exec a.out, and all the Cocos detailed kernel level statistics will show up in the profile, just because there's a handshake between Cocos and tau.